We're going live. Live in the beehive. I'm going to be a little bit rusty on Twitch, but let's see if this sounds good. We're going live. Live in the beehive. I'm going to be a little bit rusty on Twitch. Okay, there we go. That sounds all right to me. I'm going to mute this. I'm going to pop out the chat. If you're joining the chat, please let me know if the audio is okay. And I'm going to put this over here, minimize this, and then we'll go over there. Okay, beautiful. Chat is popped out. I need to work out how to get the chat over the stream. Is that a thing or is that too distracting? It doesn't matter. So, hello everyone. Welcome back to another stream. This is very exciting. What we're going to do today is some PyTorch deep learning. I am working on a new course. It is still a work in progress. However, we're making some significant progress. I'm up to notebook number 4, and I've got 1, 2, 3, 4. I'm probably going to do another 5 notebooks after 4. But we are now up to PyTorch Computer Vision. All the materials will be on my GitHub. You can see it here, PyTorch Deep Learning. Otherwise, LearnPyTorch.io will be the book version of the course. And here's notebook number 3. This is what we're going to be working on. Well, so the course is going to go through all of these steps here. What we're going to be doing in this stream is going through the exercises and the solutions, making the solutions to the exercises live. So you can see what it's like to code solutions to these sort of problems. But here's all the code that you would have already gone through if you're doing the Zero to Mastery course. We're not going to go through all of this in this stream because, of course, that would take far too long. I'm instead going to go right down here. We could just scroll down to this and click exercises. See, here's what I have to do. I've got a little TK node here. Can you see that on the screen? Exercise template notebook for 03. Look what I've got here. PyTorch Computer Vision exercise solutions. So this is what we're going to start working through. What are 3 areas in industry where computer vision is currently being used? What is overfitting in machine learning? And write down a sentence about what you find. Search ways to prevent overfitting in machine learning. Spend 20 minutes. We're not going to do this one. We might actually do this one. Maybe not all of 20 minutes because I want the stream to be mostly about coding. So we are going to do some live coding in this stream. Let's see if we can get through all of these 13 exercises. Now, of course, the GitHub is where this code is going to live. If you want this notebook, it's going to be in extras, PyTorch Deep Learning extras, solutions, and then notebook number 3, which is this one here in Google Colab. But of course, this is on GitHub. By the time that we finish this stream, hopefully we have a bunch of code in all of these cells. So let's get started. I'm just going to start coding. Jupyter Lab, I've been using that. Oh, here is what I have to do. So this is what we're doing today, in progress. Make exercises and solutions for 03. Let's get started. By the way, all of the exercises here are based off module number 3 in the PyTorch or Zero to Mastery Learn PyTorch for Deep Learning course. Coming soon to an online course platform near you. So we'll start off by checking for a GPU. And so yeah, this is what the TK is. TK is basically to do for me. I use TK because you don't see the letters TK often together in a sentence. But we're making a live walkthrough of all the solutions and errors. This will be on YouTube. I'm currently on Twitch right now, but it'll be on YouTube after I'm finished. So we're going to check for a GPU, NVIDIA SMI. If you don't have a GPU in Google Colab, what can you do? You can go to runtime, change runtime type. Let me just do that again. Runtime, change runtime type. It starts off at none by default, but I'm going to select GPU, click save. I am paying for Google Colab Pro. So, oh, hello. We have someone here from Peru following me for almost a year. Thank you so much. I appreciate that. But I was saying I'm paying for Google Colab Pro, and that gives me access to quite a fast GPU. So there is a free version of Google Colab, but I found enough value to pay for it, so therefore I pay for it so I get a faster GPU. Now we're going to import PyTorch. We could just write all this code again, but import torch, it's only 2 words there. The exercises are going to require a PyTorch version above 1.10.0. So this is just to make sure you have above 1.10.0. And then we're going to set up device agnostic code, which means if we have access to a GPU, we want to use CUDA as our computing device. CUDA is, what is CUDA? It's a programming paradigm for GPUs. So that's why we're using CUDA. And I'm going to get out of some windows here so that I only have what I need up there. Yeah, there we go. If we have a GPU available, otherwise we want to use CPU, which will be the default anyway. So this is device agnostic code. So now, question 1. What are 3 areas in industry where computer vision is currently being used? So, do you have any idea? If you're in the chat, what are 3 areas in industry where computer vision is currently being used? Let me start to think. I'm going to give a big one that you kind of see on the news a lot. And I can think of another one. And I can think of another one. I can think of 3 so far. I mean, there's many where computer vision is being used. But let's figure this out. So I'm going to write my answer here in text. So 1, self-driving cars. Such as Tesla using computer vision to understand or to perceive. How do you spell perceive? Perceive what's happening on the road. We have another offering from the chat from Pepe Parker. Healthcare imaging, beautiful. So healthcare imaging, such as using computer vision to help interpret x-rays. I also saw Google computer vision for bowel cancer or polyps. Yes, here we go. Improved detection of elusive polyps by machine learning. Beautiful. So this is a computer vision, a camera goes into your intestine and recreates a map of what's in your intestine. This is a really cool use of computer vision. Look at that. And it's detecting polyps. So can you see that on the screen? I think you should be able to. I might zoom in a bit. And so polyps are small growths on the intestine wall, and they can potentially become, is it carcinogenous? Is that the word for cancerous, or just bad? They can become bad. And so if you can detect these and remove them, well, then it potentially prevents someone from their health deteriorating. So that's a really cool use of computer vision. So I'm going to put this in there as well. Google also uses computer vision for detecting polyps in the intestines. And number 3 is, I might put in here, see Tesla AI Day for more. There's a great video of Tesla AI Day where you can see how they use computer vision for their self-driving cars. So that's Andre Karpathy, head of AI at Tesla. I'm just going to mute this. Yeah, Tesla Vision. Here we go. So this is a biological cortex. So that's our vision system as a human. Very, very advanced system developed over thousands, maybe millions of years of evolution. And so, look here, detection head, this is what happens. We've got a picture comes in here, goes raw. It goes through a regnet, which is a regularizer net, regnet, computer vision. This is the sort of thing, right? The most flexible network architecture for computer vision. Right, there we go. Tesla are using things like this that we all have access to. It goes through a classification head and a regression head, and it classifies what objects are in this picture. And then if we go through, Tesla combine 8 different cameras to create a 360 operation of what's happening. There we go. So per camera vision. Then they fuse them all together. But I'm just going to link this in here. computer vision. So there's no shortage of things going on here. And then we have another suggestion from the chat. Thank you. We have Mitanshu says security. So security. Computer vision can be used to detect whether someone is invading your home or not. And so I believe there's security cameras here. So Google security camera. What is it called? I think it's called the Nest. Now, I live in Australia. Apparently these are available here. Yeah, vision. Night vision. Where's the product page for these things? Nest. Camera. So I think I've seen on these product pages already that, yeah, you connect this camera. It goes on your outside of your house, powered by batteries. Oh, do we have an alert? There we go. Okay, yeah, so you can select an area of your property of where you'd like to be alerted if something goes in that zone. Intelligent alerts, person seen. So this is pretty cool, right? Computer vision, we've got three areas in the industry where it's been used. So we've got a motivation for using computer vision. We have many different use cases here. So now I'm just going to copy this. There. 3 areas of industry where computer vision is currently being used. And Mitanshu says many researchers are working on identifying war crime in Ukraine. Yeah, so there's an example, another example. You could use it for identifying war crimes. You could identify strangers walking into your house. So many different things. Basically, if you can visualize it in the form of a picture or a video, you can use computer vision for it in some way, shape, or form. So, next one, number 2. Search what is overfitting and machine learning and write down a sentence about what you find. So, who wants to, in the chat, who wants to give me a 1-line definition of what is overfitting? I'm just going to exit out of these extra tabs. What is overfitting and machine learning? And by the way, there is a section in here. Do we have what is overfitting? Overfitting. Oh no, we don't, but that's all right. We cover overfitting in... Overfitting means it's learning the training well. Oh, there's a typo there. But those patterns aren't generalizing to the testing data. So I'm going to update this notebook on the fly so we can correct a typo here. I'm just going to go into Jupyter Lab. I fluctuate between using Jupyter Lab and Google Colab for my work. So I want to open up here. Oh, computer vision for capture. Yes, that could be an option as well. So let's find overfitting. I'm just going to correct a typo in this notebook. Overfitting means our model is learning the training data well, but those patterns aren't generalizing to the testing data. I'm just going to update this notebook. Push that to GitHub so the changes are reflected in the book. Git status, git pull, git add 03, git commit, fix typo. So, has anyone looked up what is overfitting in machine learning yet? Let's find out together, hey? Oh my goodness. Google Chrome just quit on me. Hello everyone, I'm back. Can you all see what's going on now? Excuse me. Google Chrome just quit on me. So what is overfitting? We buffering here. I'm just going to, I think Dropbox is uploading. I just turned off uploading. I'm back. Let's look up Wikipedia for overfitting. In statistics, overfitting is the production of an analysis that corresponds too closely or exactly to a particular set of data and may therefore fail to fit to additional data or predict future observations reliably. So if you're in the chat, let me know if everything's going all right. I just paused some uploading that's happening. But essentially, this is what overfitting is. So I'm just going to get out of what's going on here. Get out of that. Yes, Matanshu, great definition. I'm going to write down Matanshu's definition. So overfitting is like memorizing for a test, but then you can't answer a question that's slightly different. In other words, if a model is overfitting, it's learning the training data too well. And these patterns don't generalize to unseen data. All right, so overfitting is your model is, it's too good basically on a specific set of data. But what is the whole premise of building a machine learning model? It is because we want to build a model that is able to predict on data that it has never seen before. So yes, we want it to learn patterns in one set of data, the training data, but we want to be able to use those patterns on data our model has never seen before. Otherwise, they're quite useless. So number 3 is search ways to prevent overfitting in machine learning. Write down 3 of the things you find and a sentence about each. So who knows 3 ways, it could be anything, to prevent overfitting. I'll give you a minute in the chat to answer this. So ways to prevent overfitting. And by the way, if you're in the chat, please let me know if the stream is going all right. Overfitting in machine learning, what is it and how to prevent it? This looks like a good thing to find out. And by the way, this is actually how I figure things out. I just Google them. If I have a question like this, I just Google them and read about it, and then I pick another resource back on Google and see something else. And then figure out where the overlaps are. So, okay, heap of examples of what's going on. Yada, yada, yada. Goodness of fit. Overfitting versus underfitting. The bias variance trade-off. So, high bias, low variance. That means the arrows, low variance means the arrows aren't really spread out. High variance means the arrows are spread out, but they're kind of, they have a low bias. So, they're also on different sections. Whereas the high bias, they're kind of all together, but they're outside the ideal target too. How to detect overfitting, how to prevent overfitting. This is what we want. Cross-validation, okay. So cross-validation is a powerful preventive measure against overfitting. The idea is clever. Use your initial training data to generate multiple mini train and test splits. Use these splits to tune your model. Okay. So that means rather than create just one training and test split across our whole data set, cross-validation means we create multiple different versions of training and test data and compare them or train a model on each of them and then evaluate the model on each of those separate test sets and see how it goes. Train with more data. Remove features. Early stopping. Regularization. Oh, here we go. So Pepe Parker says 3 ways to prevent overfitting is regularization techniques. use a different model, and reduce noise in data. I like that. I'm going to take all those three. Otherwise, you could read more here. I'm going to just link this in here. So text, see this article for some ideas. And then we'll go three ways to prevent overfitting. And this is from Pepe Parker 22 on the Twitch chat, so thank you very much. We have regularization techniques. What are some regularization techniques? I'll give you a second to give an answer, and we'll come back to that. Use a different model. I might be able to help here. So if we want to use a different model, we go, maybe the model you're using for a specific problem is too complicated. As in, it's learning the data too well because it has so many layers. You could remove some layers to simplify your model, or you could pick a totally different model altogether, one that may be more suited to your particular problem. Or you could also use transfer learning, taking the patterns from one model and applying them to your own problem. So how would you find out about transfer learning? You could go, what is transfer learning? Transfer learning, beautiful. I'm just going to link this in here. That's going to be extra curriculum for you if you'd like to look that up. We're going to cover transfer learning later on in the course, in Notebook 06 specifically. So we're still waiting on some regularization techniques. We'll come back to that in a second. But number 3 is reduce noise in data. This is going to help us prevent overfitting. Maybe if we wanted to reduce the noise, I think we could increase the noise to reduce overfitting. Because remember, overfitting is our model is working too well. So it's kind of learning the noise in the data as well. So we could go reduce noise in data / clean up dataset / introduce data augmentation techniques. If the model is learning the data too well, it might be just memorizing the data, including the noise. One option would be to remove the noise / clean up the data set. Or if this doesn't work, you can introduce artificial noise through the use of data augmentation to artificially increase the diversity of your training data set. And then we have regularization techniques. Ridge or lasso are the only ones I know at the moment. That is one option. Are they mentioned in here? Ridge or lasso. We got dropout in here? Yeah, okay. So this is probably what I would go for if we're focusing on neural networks, is you could prune a decision tree or drop out on a neural network. So dropout's probably one of the most common neural network regularization techniques. So you could use dropout on your neural networks. Dropout involves randomly removing neurons in different layers so that the remaining neurons hopefully learn more robust weights patterns. So we'll go dropout machine learning. We'll just link to dropout as well. Dilution, also called dropout or drop connect. let's put this in here. Beautiful. I think that is enough. So we have regularization techniques. We have use a different model. And we have reduce noise in data, clean up the data set, or introduce data augmentation techniques. Wonderful. I think that is enough for that. Now, number 4 is spend 20 minutes reading and clicking through the CNN Explainer website. Upload your own example image using the upload button on the website and see what happens in each layer of the CNN as your image passes through it. So let me just find my own... Oh, that's a little spoiler of what's coming in the course, or what you may have already seen if you're watching this video at a later date. After watching the course, I'm just going to find an image that I can use. Images. Let's go. Do we have the Cybertruck? Yes, I do. Okay, I have the Cybertruck ready. So let's go to, I want my chat back. What I'm going to do is get out of these 3, and then we'll go to the CNN Explainer website. So this is a great resource for learning about convolutional neural networks. And it works in your browser. So we've got 10 different images up here. And what it's going to do is create a neural network live in the browser to predict what's in these images. So if we click on this, ladybug, the neural network is predicting ladybug, which is correct. Do we have pizza? Yes, we do. We have pizza here. We have an image of peppers, bell pepper, and then we have school bus. It's predicting there. Not sure if you can see this properly. It's close enough. And so what's going to happen here is the input. This is a 64 by 64 image with 3 color channels, red, green, blue. So 64 is it's a square image, and it's got 64 pixels wide and 64 pixels high. And then of course, because it's a color image, it gets broken down into 3 different color channels. There's a pixel value for red, a pixel value for green, and a pixel value for blue. And if we combine all of those different values, we get this image here. Now, how many color channels would there be if it was a black and white image? So I know this is not very zoomed in, but I think it doesn't actually zoom in. Oh, does it? Yeah, it does. My bad. So what would we have for a grayscale image? We'd have 1 color channel because we have black or white pixels. And so then it goes through a convolutional layer here. And in this case, we've got 10 hidden units. And so it reduces it down to 62. And that's going to be a theme throughout this entire network here. I'm just going to move my face. We're spending about 10 minutes on this website here. As it moves through the network, what the whole objective of a neural network is for data to go in, and then the neural network is going to learn a compressed representation of whatever's in that data. And so that's why you'll notice that, and what I mean by compressed representation is, why compressed? Well, because a compressed representation is portable. If you just memorize the exact data that went in, well, that wouldn't be helpful for you at all, right? Because you might as well just take around your entire data set all the time. The benefit of compressing it into a neural network, giant weight matrix, is that you can move that around and use it for other different types of data. So it's smaller than the original data set. That's the ideal. But it holds, the compressed representation holds a great representation of your original data set. So you could, in one hand, say that intelligence is compression from the point of view of a neural network. And so we pass our input in. It goes through a convolutional layer. This is conv11. It gets reduced in size by 2 pixels on the height and the width. So 62 by 62. We've got 10 different hidden neurons here. It goes through a ReLU activation layer. We're going to see this coded out in a second. And then it goes through another convolutional layer, a little bit more compressed again, from 62 to 60 60. Goes through max pooling. So max pooling takes the maximum of a different section of the image. So it further compresses the image from, it halves it here basically. So now by the time we get to this layer here, our image has gone from 64/64 to 30/30. So we've halved, more than halved the representation of our original image. And then by the time we get to the end, this is going to let me scroll. I can't scroll on this. All right, I'm going to have to zoom out. By the time we get to the end of this max pool layer here, we're feeding in a representation of 13 by 13 into our final layer. So we went all the way from 64/64 to 13 by 13. And that gives us, we put an output here of 10 different classes because we have 10 different types of images. If we had 20 different classes, this might be 20. If we had 100, this might be 100. So the whole idea here is take your inputs, turn them into numbers, pass them through some form of combination of neural network layers, compress the representation, learn the representation of the original data, and leverage that in some way that allows us to put data in and intelligence out. So this classification is a form of intelligence. Whatever your definition of intelligence, we now have a neural network that can classify certain images into 10 different classes of objects. Now, of course, you could scale this up depending on what problem you're working on, but 10 is a good number to start with. So what is a convolutional neural network? In machine learning, a classifier assigns a class label to a data point. For example, an image classifier produces a class, e.g. bird or plane, for what objects exist within an image. We've seen that if you've gone through the videos of the course. And so a CNN is a neural network, an algorithm used to recognize patterns in data. That's what we're doing. We want to build neural networks to put numbers in, get patterns out. Neural networks in general are composed of a collection of neurons that are organized in layers. So all of the neurons and all of the layers are some form of mathematical operation. Now, a convolutional layer has a defined mathematical operation. A ReLU layer has a defined mathematical operation, if you could call it that, because ReLU is kind of just a very simple, is the input negative? If it is, turn it to 0. If it's not, just let it go through. But that's how you can think of neural network layers. There's some form of mathematical operation that works on tensors. Now, a tensor can be thought of an n-dimensional matrix. When we put our data into our neural network, we convert it into a tensor. That tensor is a numerical representation of the data we put in, regardless of the data that goes in. Whether it be an image, whether it be text, whether it be audio, we turn it into a numerical tensor of some dimension, whatever dimension is fitting for our particular data set. And then that dimension, or that tensor, gets passed through these neural network layers, a conv layer, a ReLU layer, a conv layer, a ReLU layer. We could stack these together in almost any way, shape, or form, as long as they don't error. Whether it learns something is another question. I mean, that's a big area, active area of research, is how to best stack these layers together. And so let's keep reading. Number 2, a neuron can be thought of a function, see, a mathematical function that takes in multiple inputs and yields a single output. The outputs of neurons are represented above as the red to blue activation maps. So we've got in here, red to blue, different neurons are associating with different pixels in the image here. So we've got red and blue. Personally, I've never really taken much interest in what activation maps get produced by these. This means, like, say this image goes in here. An activation map is this little depiction of what we've got there. For me, they don't really mean much to me. They might mean much to someone who wants to dig into the weeds of what each single layer and each single neuron is learning. But for me, they just, I don't gain much of an understanding by looking at those. For me, it's more so what manipulations are happening to the shapes of my data as it goes through a neural network, and how do I get it to output the things I want on the other end. That's what, for me, that's what helps my understanding with a neural network. A layer is simply a collection of neurons. So if a neuron is if some sort of operation, a layer combines multiple neurons to do with the same operation, including the same hyperparameters. So a hyperparameter is what? A hyperparameter is a value that you can set in your own neural network. So typically layers learn parameters. Now a parameter, the difference between a parameter and a hyperparameter, a parameter is a value that a layer learns on its own due to its function and due to its input data. So a parameter, in other words, a weight, in other words, a pattern, is something that the neural network learns on its own, whereas a hyperparameter is something that us as data scientists or machine learning engineers will set. So number 4 is kernel weights and biases. While unique to each neuron, are tuned during the training phase and allow the classifier to adapt to the problem and data set provided. So this is what our model is learning under the hood. Kernel weights and biases. There are lots of different names for these. I've just called them parameters. Probably the most correct name is weights and biases. So each layer will have its own collection of weights and biases, and they will be adjusted as data goes through the neural network. Now, what is weights and what is biases? Weights is typically a matrix. So just like our data gets turned into a matrix, each layer has its own weight matrix. And the same thing, each layer has its own bias vector. And what we're trying to do, the whole premise of a neural network is to pass in data, whatever data we're working with, images, text, audio, and pass it through these layers. And then with the help of a loss function and an optimizer function, the weights and bias values of each of these layers get adjusted to represent our input data. And then those learned representations, the learned weights and biases, can be used to put data in and have intelligence out. That is the whole premise of neural networks. What do we have here? The specific values can be viewed in the interactive formula view. Oh, let's have a look at that in a second. A CNN conveys a differentiable score function. So that's a loss function, which represents as class scores in the visualization on the output layer. Well, it might not be a loss function. They might be using some other different terminology, but essentially that's what we're trying to do. We have a loss function, which measures how wrong our network is, and we're trying to minimize that loss function, in turn increasing how right our network is. So let's dive into one of these and have a look. With a convolutional layer, what's happening? We have a little kernel that's going to pass over each square of our image, and it's going to go in. We're going to add a bias term here, and then we're going to have some little oh, let's click on this and see what happens. Oh, there we go. Okay, so this is, well, now we're cooking with gas, everyone. I'm going to move myself up here. So we have a convolution here. Now, this is the beauty of going through this amazing website for 20 minutes, is we can see what's going on. You could spend more than 20 minutes on here, by the way, and just a heads up, we're still on exercise number 4. Spend 20 minutes reading and clicking through the CNN Explainer website. So we have our input. Watch what happens to the numbers as I manipulate them. As I move this little square around, we're going to have a change in numbers. Oh, look at all those numbers change. And then they output to something on the right. So this is what's happening inside our neural network. Now, you could dig deeper into the weeds here, but this is the entire premise of neural networks. If we have some input data and we manipulate it in some way, shape, or form with a convolutional layer here in our case, and we have all these different little feature activations, and we add them all up and multiply them, and we get this value here. And this value corresponds to this single pixel over there. And because of the size of this convolution, we get a reduced size in the output. Remember how I said we're trying to compress our data as it moves through the network, but still retaining a valid representation of it. So if we clicked on any one of these, they're all doing the same thing, but just on slightly separate processes. So there's a ReLU activation. Remember how I said ReLU is quite simple? If something's negative, it just takes the max of 0 and that value. So if the value here was negative, the max is going to be 0. So it just zeros everything that's a negative value. Do we have any zeros? Oh, there's a negative. Beautiful, see? Outputs there. So this is, I'm not going to go through this whole website because I think it's very valuable that you go through it yourself. So I feel like that's enough. We've covered the basic premise of what a convolutional neural network does. We're going to code one up in a second. We've seen this throughout the course. If you're watching this later as me going through the exercises. But here you can go into deep dive into what each layer of the network does. The input layer, the convolutional layers. Then we have that same operation that we just saw before. Then we can understand the hyperparameters, change the input size, change the number of padding that we have, change how big the kernel is. The kernel is that little square that moves over the image. And change how big the stride is. The stride is how many steps the kernel takes at a time. So right now our stride is 1, so we can just take 1 step. 1, 1, 1, 1. And you see what it's doing. It's compressing the 3x3 red square in the middle here to that one red square. If I move my mouse, it's going to... Oh, there we go. So the 3x3 red square here is getting compressed into this one square here. And then if we move this one along, it gets compressed into there. Then if we move this one along, it gets compressed into there. So that is the theme throughout the entire convolutional neural network. Then we have padding, kernel size, stride, activation functions. I'd encourage you to read through this entire page on your own if you'd like to deeper understand what's going on behind the scenes of the PyTorch code that we write when we're writing convolutional neural networks. So the CNN Explainer website is a great insight into all of the nuts and bolts of a convolutional neural network. Okay, and so now we're up to exercise number 5. Load the torch. Let's get some data, right? Because what is this? What is the first step of basically any machine learning model is that, well, number 1 rule of machine learning is don't use it if you don't need it. But second rule is if you don't have any data, well, you can't really build a model. So we need to get some data. We're going to get, because we're working with computer vision, we're going to use Torch Vision datasets. That's going to give us, we'll get Torch Vision, and we will go from Torch Vision, import datasets. We're going to get the MNIST dataset. So let's write some code here. Get the MNIST dataset. So let's see if we can go train data equals datasets dot MNIST. Do we have a doc string here? Yes, we do. Root can be, we'll just get it into the root file, or we'll just get it into the current working directory. Or maybe, do we want a data folder? We'll see what happens if we download it into the current directory. Train equals true. Do we have another doc string? And so we want to download equals true. And then we want the transform equals none. Should we transform it? What is a transform? So a transform, do we want to transform the data as we download it? How about we do that? So we go from Torch Vision, import transforms, and what I'm going to do is I'm going to transform the data because we want our data in what form. If we start with images, if we start with any form of data, before we pass it through a neural network, what do we have to do? Well, we have to convert it into a numerical representation. And what form of numerical representation does the images here come in? Well, they get converted to a tensor, which is basically the same as every other form of data. It gets converted into a tensor. So let's use the transform. We're going to convert our data transforms.toTensor. Okay, we're going to see if this works. So get the MNIST. We want the test data set now. Test data set. Train data set. Test data equals datasets dot MNIST. And can you guess what we have to do now? So root equals the current directory. Train equals false because we don't want the training data set. Download I'm going to set to true. And the transform I'm going to call PyTorch transforms.toTensor. And this is going to convert our MNIST images into tensors. And if we want to have a look at PyTorch MNIST, we got this here. So datasets, built-in datasets. Is MNIST here? MNIST. There we go. MNIST dataset. Do we have a link to it? What does it look like? The MNIST database of handwritten digits. So you might have seen this already. I'll just get the images up. There we go. So what we're trying to do is we're going to build a convolutional neural network to try and identify what digits are in an image. Nice and simple. This is like the hello world of machine learning. Can you build a machine learning model to recognize handwritten digits? Well, let's try out, hey? There's a number of different places we can get this data set, but because we're using PyTorch, we're going to stick with PyTorch. Let's see if this code that I've written works. If in doubt, run the code, right? So what does our train data look like? And test data. Beautiful. So train data, we have dataset MNIST, number of data points. We have 60,000 training samples, and we have 10,000 testing samples. So if we go train data, what does 0 sample mean? Beautiful. Okay, what does this give us? Okay, so I think this is an image and a label. So our image is currently in a tuple. So let's write this down. Data is in the form image label is in tuple form image label. So if we get train data 0, 0 and train data 0, so the 0th sample, so the 0th sample of train data, and what if we get, can we get the shape of train data? No shape. Can we get length? Okay, there we go. Test data. So we're exploring the data here, and this is what you're going to have to do with your own problems, is explore it and see what happens. So let's just print it out. So I believe this is an image. So image, print, image. And this is what I do at the start of every problem, right? I just print out a whole bunch of different things and become one with the data, as Andre Karpathy would say. Excuse me. Label. By the way, it is Good Friday where I am, so wherever you are in the world, happy Good Friday. Whether you are religious or not, I believe it's good to just celebrate a day, celebrate being alive. So we have an image, is in the form of a tensor. Why is it in the form of a tensor? Well, because we use the transforms to tensor. So we've now got a data set. We've got a training data set, we've got a testing data set. What's the whole premise of a training data set? It's so that we can feed our model over the training data set to learn patterns that will predict on the testing data set. So now let's plot an image. What does this say? It says load the torch vision datasets, MNIST, train and test datasets. Okay, I think we've done that. Wonderful. Let's go to the next one. Number 6. Oh, we're nearly halfway through already, everyone. This is exciting. Visualize at least 5 different samples of the MNIST training dataset. Oh, by the way, we can get the class names from the dataset. So class names, what do we have? Equals train data classes. Beautiful. Okay, so our class labels are in integers, which is okay for us because we do want our model to predict an integer. You might think that this might be a regression problem because we're trying to get our model to predict a number, but in our case it's classification because we're trying to classify 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 as separate classes of images. So all of these images are 0 and all of these are 1. Can I zoom in on that? Yeah, there we go. All of these are 0, all of these are 1, All of these are 2, 3, 4, etc. You get the point. We have a question here. Are we identifying handwritten numerals from writing we know are numerals, or from writing which could be but are not required to be numbers? So you could feed this neural network any handwriting that we're about to build. However, it will only predict on 0 through to 9 because that is what it is going to be trained on. So the network that we build, this is an important point, will only be, so good question, unstable juice, I appreciate that. The network will be focused on handwritten digits. So this original data set was for, I believe, American postage system or something like that. So they wanted to identify postcodes on handwritten letters. So you could put the letter through a scanning machine and it would take a photo of the label, the handwritten label, and then would identify what postcode was written based on the handwritten digits, and then it would sort the letters into the area of the post office. I'm guessing, I might be making this up here, but this is my MNIST history, what my brain's telling me, of where that letter should go. So I believe that's where it started, this whole premise. And now we are here, I believe this is almost 30 years old. So we're here 30 years later doing the same thing. 1998. So what's that? 24 years ago. So let's visualize some different samples. So remember, how about we import matplotlib .pyplot. So whenever you want to visualize, matplotlib is one of my go-tos because our numbers, our data is in what? Numerical form. Tensors representing images. So let's plot 5 images. So for I in range 5, print I. So we're just going to loop over this. And then we want image equals train data I 0. And label equals train data I1. And then we're going to go plt.imshow image, plt.title. We're going to use the label as the title, and plt.axis. We're going to turn off the axes. What does this look like? Invalid shape for image data. So I'm just going to set this up here. Watch this. This is a big issue in machine learning and deep learning in general, is what shape is your data? I'm just going to put this into here. Now the benefit of doing this live is that you get to see how I explore data sets from scratch. Wonderful. Now let's get our image shape and our label shape. Int has no shape. Okay. So our image has a size or a shape of 1. So that's color channels, height, width. However, matplotlib's imshow function can only deal with color channels. So this is, let me just write this down. Check out the shapes of our data. Print F, image shape. wrong shapes of data is possibly one of the biggest errors that you'll run into in deep learning. So this is in the form color channels, height, width. So this is just the default way that PyTorch represents image data. Label. Now this is no shape due to being integer. Integer, 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 integer. And then, so there's two ways, really two agreed upon ways in the field of machine learning of how to represent image data. So color channels first, which is CHW, so color channels height width, or let's go here. Note, there are two main agreed upon ways for representing images in machine learning. So one is color channels first. So this is CHW, which is color channels height width. Let's go like that. And I'm going to write this down, CHW. And then two, color channels last. Oh, I put them first. Height, width, color channels. So this is very important to know. Why? Because how you represent your data is going to follow you basically wherever you go. Now, this is PyTorch default as of April 2022. And this is, however, the confusing thing is this is matplotlib / TensorFlow default as of, now I write this as of April 22. Why is that? Because it's April 2022 now. But these might change over time. A lot of things do. The way the research field is going right now is that this is color channels last is generally the accepted method to be most efficient in terms of computation. I'll let you get into that rabbit hole yourself, but this is what's causing our error here, is that because our image, let's print our image shape. Because our image shape is color channels first, it isn't working with matplotlib, because matplotlib expects our images to come in when we use imshow to be height, width, color channels last. So we need to permute, which means reorientate our images axes. So we can swap the axes. So what this means is that we're going to put dimension 1 coming first, then dimension 2, which is this value here, coming second. Finally, we're going to take dimension 0, which is this one here, and put it at the end. So that's what permute does there. So maybe we go image permute equals image.permute 1, 2, 0. And then we're going to plot image permute. And we're just going to, I'm just going to print this out for demonstration purposes. But this is, it's an important step to be aware of. Oh, what did we get wrong? Incorrect shape for image data. Oh, we might need to squeeze it as well. Okay. Maybe we go, let's try to squeeze it. I'm working this out on the fly, team. There we go. Okay, beautiful. So this is what we did. Did we get print image permute.shape? We actually got rid of the singular dimension. I will show you this. We're a bit all over the place at the moment, but that's okay. This is what you're going to be actually doing when you code these sort of things and becoming one with the data. There's no set way of working all of this stuff out. It's not like you approach a notebook and you know exactly what you're going to code beforehand. That wouldn't be too fun, would it? Have I got a typo? Yes, I do. Standard. Okay, there we go. So we go from each time we have one image, and then we use the squeeze function to get rid of the single dimension, because then doing so means that our image is compatible with matplotlib. So just keep that in mind. Matplotlib prefers color channels last, or if your image is grayscale, remove the singular dimension, and Matplotlib can handle that. That kind of takes a little bit of practice to understand. I might just create another plot here. Plot.figure, fig size equals 5.5. Okay, that's too big. 3.3. There we go. So this is what we're dealing with. And this is a different color to the data that we've seen before, and that is because, what if we go C equals gray? Grayscale. I'm not sure. Let's figure it out. Matplotlib, how to get gray images. CMap. Okay. This is how I figure these things out, right? The beauty of this is that you're seeing it live. CMap equals gray. I thought it was something like that. There we go. Okay, so we have grayscale images of different numbers. 5, 0, 4, 1, 9. So now do you see how our data looks kind of similar to the stuff on the CNN Explainer website? So we have an image here. It has some sort of height and width value. In our case, our images aren't color, so they only have one color channel, but they still have a pixel value. So what we're going to be trying to do is building a convolutional neural network to do this exact thing here. To go over our image and to create activations over here that are some sort of learned representation of what's in the image over here. And then repeat that step over a number of different layers till finally we have an output layer that is going to output different classes of handwritten digits. Let's keep moving forward. Exercise 7. Turn the MNIST train and test datasets into DataLoaders using torchutils.data.dataloader. Set the batch size to 32. So what is a data loader? Well, we have a data set. A data set is just a big chunk of data, whereas a data loader is generally in computing, or especially in neural networks, because you can deal with, I'm just going to pour myself a tea here. Because in neural networks, you can deal with hundreds of thousands, millions of examples, and billions in the case of modern neural networks. However, computers don't have infinite memory just yet. So when we turn things into data loaders with, say, a batch size of 32, why 32? Because 32 is good for your health. Said by Jan LeCun, who actually created the MNIST dataset. Jan LeCun on Twitter. Training with large mini batches is bad for your health. More importantly, it's bad for your test error. Friends don't let friends use mini batches larger than 32. So this is a few years old now. Of course, people use batch sizes a lot larger than 32, but 32 generally works pretty well with smaller problems at whatever you're working on. The benefit of this is, one, we're not forcing our computing hardware to compute on every single example we have in one hit. That might crash our computer because it runs out of memory. So we compute on 32 different samples at a time thanks to our data loader. It turns our data set of 60,000 examples into whatever 60,000 is divided by the batch size. So divided by 32. It turns it into 1,875 smaller groups of 32. So our neural network will compute on 32 samples at a time, and then it will update its internal patterns on those 32 samples at a time. And so the benefit of this is twofold. One, it computes on a smaller number of samples, so it's uses far less memory than the entire sample here, 60,000 samples in one hit. And two, it's updating its patterns more often. So it updates its patterns every 32 samples rather than every 60,000 samples. So that's the benefit there. Let's create a train data loader. So create train data loader. So we're going to go from torch.utils.data, import data loader. And of course, we could look up the documentation for this, PyTorch data loader. What do we get? Torch.utils.data. Data loader, this is what we want. So we need to pass it a data set, which is what we created, a batch size. Do we want to shuffle the data? Why would we shuffle the data? Because again, we're trying to, rather than our neural network memorize order, so say for example, our handwritten digits are all in order of 0, 0, 0, 0, so 10,000 images of 0, 10,000 images of 1, 10,000 images of 2. We don't want our model to just memorize the order. We want to shuffle these up and make it harder for our model to understand. So that way, it can predict on any order of numbers that come in the future. And then there's a few other things that you can go through if you'd like. Pin memory, so some things to help with the computing. So if we pin the memory is going to be persistent on our GPU. But a few things that are probably outside the scope of what we're covering for now. So I'd highly encourage you to read through this documentation. If you don't get it all, that's completely fine. I don't get it all. But that's what the point of documentation is. It's not for you to get it all. It's for you to use as a reference, to know where to look for something. There's no way you could remember every single little thing about PyTorch. Look at this. The point of a library, I've got a library over there. It's quite empty at the moment because I'm moving house soon. But the point of documentation is not for you to store it all in your brain, right? Because no person could do that. It's so that hundreds of people can write down what they know so that if you want to look something up, you can look it up. The same thing with books on a library. I don't remember every single passage in all the books over there on my library, but if I'd like to look something up, I just pick up a book and I scroll to whatever page I need to look at. So that's the beauty of documentation. Let's create a data loader, train data loader. What do we need to put in? So we need, I'm just going to run this so we have data loader imported. Data loader, do we have a doc string? Yes, we do. By the way, to get the doc string, I'm pressing Command, Shift, and Space on my Mac. If you're on Windows, it might be Control. So we need a data set. Data set equals our train data. Because remember, what is our train data and our test data? We created them before as data sets. Dataset MNIST and dataset MNIST. So we're going to pass in our train data. We're going to pass in our batch size. We want a batch size of 32. We could do whatever size we want here. We could do 100, we could do 32, we could do 16, we could do 1. But 32 is a good size to begin with. And we're going to shuffle the training data. That's all we need for that. Now let's do the test data loader. Equals data loader, data set equals test data loader, or test data. We're going to do the same batch size for the test set, and we're not going to shuffle the test data set. Why don't we shuffle the test data set? We could, but we don't actually need to, because the patterns that our model's never going to see the test data set. So I found evaluating models later on, it's more helpful if the test data set is in the same order each time, so that your evaluations can be done on a data set that's continually in the same order. Learning the patterns is more important that the data set is shuffled. So just keep that in mind. Jared says, never been a fan of books, always found I can just Google the answer for free. You're totally right. Google's a tool just like a book. One is free, the other isn't. Yeah, you're totally right. So Google is free. However, if it is free, you're the product. So yeah, I personally like to just read books. I get distracted if I'm on computers. So I like to read books end to end on different things, and then probably never go back to the book again, just know where to Google from there. But I like to use books as a foundation of knowledge. So now let's have a look here. We've created train data loaders, or train and test data loaders. Let's have a look. What do they look like? Beautiful. So look what we've got. Torch utils data.dataloader. Now if we go next, which is step through the next step of the iteration in train data loader, what do we get? Beautiful. We get 32 samples. So I wonder if we could do this. For images, labels in next, print images dot shape, print labels dot shape. Is this going to work? Oh, we can't iterate through it. For sample in next, and for image label in sample. Let's check out what's in our data loader. Too many values to unpack. Expected 2, got 1. Let's just print the sample. Print sample. Wonderful. Okay, so we get a tuple. Is this a tuple? I always get a little bit confused when I'm iterating through these. Okay, there we go. So we have 32 images, right, of one color channel, 28 by 28, and we have 32 labels. Yeah. Unstable juice gets, I get more useful information out of a dead tree book instead of an electronic book or page. Personal preference, yeah. I'm the same. I like paperback books. So now let's have a look at the length of our train data loader. In each of these, we will have 32 samples. And we'll also get the length of our test data loader. Beautiful. So we have 1,875 batches of training data of 32 images paired with 32 labels. And we have 313 batches or mini batches of test data of 32 images and 32 label pairs. So now what is our goal here? We would like to train a model on the training batches to learn patterns that can predict on the test data set. So the data, our model will never see the test data except if it's trying to predict on it. So we're going to recreate model 2 used in this notebook or used in notebook 03. The same model from the CNN Explainer website, also known as Tiny VGG, capable of fitting on the MNIST dataset. So let's create a model here. Let's see if we can just recreate it from the website here. So we have an input. Where's my face? Up in the top right. I might move myself down to the bottom. There we go. Okay, let's recreate model 2. And so if you wanted to recreate model 2, where could you go? I'm just going to get out of all this. You could go to 03 PyTorch Computer Vision, and I'll just open this so that we've got the table of contents. Model 2 is this one. Building a convolutional neural network. So this is exciting. We're going to build our first convolutional neural network. If you've been through the course, you would have already built some, but we're going to build the first one with PyTorch on the stream. That is exciting. So here's a convolutional neural network. This is the model we're about to build. And so this is, if you broke down the architecture of what's going on, it's the same as what's happening in here on this website. So we've got a convolutional block, number 1, a convolutional block number 2, and then a classifier layer as the output. And then we have a forward method. But that's enough talking about that. This is what you could use as reference, this notebook here. But let's just try and build it from looking at the website. So class, what can we call it? MNIST model. And I'm going to inherit from torch.nn.module, because basically every model in PyTorch inherits from nn.module. So let's write down here what this is. Model capable of predicting on MNIST dataset. And so we're going to go def init self, and then we're going to put in here, we want input shape, which is going to be an integer. We want hidden units, which is how many. So in this case, there is 10 hidden neurons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hidden units. So these are all going to be what? They're all going to be a small mathematical function to try and learn the representation of the input data here. So we're going to set this up as an int as well. And then we want output shape. Remember, much of machine learning is about defining the right shapes of things, input and output shape. And so is that visible? Close enough to being visible. And we go super dot underscore init. And now we're going to create our layers. So now let's go self dot conv block 1 equals, what can we make this? nn.sequential. And maybe we put inside here. So nn.sequential is, I haven't imported torch.nn yet. From torch, import nn. So nn.sequential is a sequential model. So it's going to step through several layers that are within its list. So we have a list of layers that's about to be in here. All sequential does is put some input data in and steps through sequentially what layers you define in here. So let's define in here, what do they have first? They have a convolutional layer here. We're going to call in nn.conv2d, and we have to define here how many input channels we have. In our case, we're going to define our input shape as that. Now the output channels, this is what I said about input and output shapes. How many input shapes do we have here? Well, in our case, we have, this one would be 3, because it's a color image. There is 3 input channels. Now the output channels is how many we're going to change that number to. So in this case, we change that to 10. So we have 10 hidden units. So input, output. Input, we have 3 color channels into our layer. Output, we have 10 in the case of this network here. This is adjustable depending on what data you're working with. In our case, because we're working with grayscale images, what will our in channels be? It won't be 3 because they're not color. It will be 1, but we can set that by setting input shape. Out channels is going to be hidden units. We can set this later on. Now what do we have next? Kernel size. Kernel size. Now what's the kernel size? What do they use here? I'm not sure. I think it might be 3. But if we go down here, we can find these are hyperparameters that we're setting in our convolutional layer. So the kernel size, if we change this to 5, look how big the red square is in the middle there on the left. Now if we change this to 1, we have a 1 by 1 kernel, or 2. 2 is the minimum. We have a square there. And then if we go up to 3, we have a 3 by 3. Then if we go up to 4, a 4 by 4. So that is the kernel. This is what's going to be convolving. So that's the word for convolving, like this, moving around our image, running mathematical operations on each of the tensors, on each of the values, and converting them into singular values over here. So that's what we define by the kernel size. What's next? Stride. Is it stride? Or stride size? Let's just look it up. I find GitHub's documentation, or Colab's doc strings aren't as helpful as just looking up the documentation. stride. Yes, stride equals 1. That's the default. Now, what's the stride? Well, let's change it. If we change it to 2, what do we get? Oh, can't do it. Our kernel jumps across 2 pixels at a time. So see here, we go over 2. Now, if we change this back down to 1, we can go 1 at a time. Now, if we reduce this, it's going to be the same thing, 1 pixel at a time. If we increase this to 3, it jumps over 3 pixels at a time. So this is a beautiful website, right? So watch what happens to our output shape as we increase and decrease the stride. Notice how the output shape gets smaller as the stride increases. So that's why you might increase the stride or increase the kernel size, is so that your output gets more or less compressed. So watch the output shape on the right. This is what happens when you change. Now increase the stride, output changed. Increase the stride, well, we can't do that, output changed. So we can manipulate how compressed our information gets through different layers by changing the hyperparameters of our said layers. So that's something to keep in mind. What else should we put on here? Padding. Now, padding, I know from previous experience that padding for this network equals 1. What happens if we change the padding to 0? Look what happens. So there's all gray squares here. Our stride is too big. And then we increase the padding to 1. Watch the outside of this box here. Watch what happens. Increase the padding to 1. There we go. So now we've got a pixel around the outside of our initial box. What does this do to the output shape? Watch the output shape on the right here. Padding down, padding up. You see there? So what does this do? Why would we add padding? Well, perhaps there's something going on around the edges of our image and we'd like our model to pick it up. So we add an extra padding around it so that we can convolve around the edges of our image and create a larger output space here. Whereas if we remove that padding, our output space is 3.3 rather than 5.5. And so again, that's just in the same light as we said before, that we adjust the hyperparameters so we can tweak the amount of compression that our neural network creates as it steps through each of its layers. Keep that in mind. So what do we have next? We go to this network. We have a ReLU layer. Okay, let's put in a ReLU layer. NN.ReLU. And what does ReLU do again? Well, ReLU, if you have a value, let's check it in. Let's just dive into ReLU. It takes the max between 0 and whatever value you put in. And so if that value is negative, it's going to be converted into a 0 over on this output here. And if that value is positive, it's going to just pass straight through. So that's what our ReLU does. And then what do we have next? We have another conv layer, and then another ReLU, and then a max pool. Okay, so let's do that. So nn.conv2d, and we can go in channels here. Now this is another important point to be aware of. In channels equals what here? So this layer is going to take as input the output of this layer here. So this is what's happening. Input layer here, inputs go into this conv layer. The outputs of this conv layer go into this ReLU layer. The outputs of this ReLU layer go into this conv layer. The outputs of this conv layer go into this ReLU layer, and so on until we get to the output. So the outputs of these two layers are going to go into this layer. So this input shape needs to line up with the output shape of the previous layer. So in this case, we're going to have hidden units as the input shape, and then the out channels, as the in channels. And the out channels is still going to be hidden units because we want 10 connections from our second convolutional layer to our next ReLU layer. And then we're going to set the kernel size. We're going to keep that as 3 equals 3, and stride equals 1. We're going to keep all of these the same as before. Wonderful. And then what do we have after the second conv layer? Well, we have another ReLU layer. Okay, we can do that. nn.ReLU. Wonderful. And then we have an nn.maxPool layer. 2D. So what is max pool? Let's have a look at the applies a 2D max pooling over an input signal composed of several input planes. Okay, so let's go back to the CNN explainer and have a look at the max pool layer. So notice, you're going to have to look at this. I'm just going to play this, and the website doesn't move with me, which is not ideal, but that's all right. Let's just play this. Watch what happens here. Notice the values in the middle. We're convolving a small kernel over the input, 6060. And in the middle, we're taking the max of whatever's inside those four squares. So 0.58, 0.74, 0.8, 0.78. So what is this doing? Well, the theory is maybe the pixel with the highest value contains the most information. So if we take that pixel with the most information, the maximum, and we compress our input by half, potentially we're still preserving the most important patterns in our image. So that's what the max pool does. It helps to compress the size of your input to, in this case, half, whilst hopefully taking the maximum of whatever section, still encoding the most important information. So that's what our max pooling layer is doing here. And then if we look at the parameters, what do we have? Kernel size, the size of the window to take a max over. So from this, it looks like we're doing a max pool size of what? We'll jump into this. We have a kernel of 2 by 2. So 2 and 2. So let's now do the same with our network here. Kernel size equals 2. Beautiful. And that's our convolutional block number 1. Now, we could just keep coding this away, but we're going to make another conv block because we have, see how the numerical here is conv11, relu11, conv12, relu12, max pool 1. We have conv21 and relu21 and conv22 and relu22 and max pool 2. So this indicates to me that they're using two blocks of similar layouts, because see how this is just the exact same as what's going on here. So they're just stacking one of these on top of one of these, and they're using the same layers in each. They're just stacking them on top. And that's kind of a pattern that you'll see in larger neural networks, is that if some concoction of layers work, stacking them on top of each other might work even better. Now I say might because that's not guaranteed either. Unstable Juice says, so the relationship between the hyperparameters could greatly affect the outcome of the CNN. How do you tune the hyperparameter relationships? I understand if this subject is beyond the target level for this stream. So how do you tune the hyperparameters? Well, that is the million-dollar question, right? Because yes, they do highly influence the outputs of your convolutional layer. However, it is quite computationally expensive to try lots of different combinations of these said hyperparameters. So you could write a program, excuse me. You could write a program to, say, build 1,000 of these models and try a different combination of values for every single one of these. There are techniques to do this, such as grid search, which is grid search. You define, like, say, a range of different hyperparameters to use, and then exhaustively go through that range of different hyperparameters to use and see which ones are the best. There's also random search, which is you just say, hey, search randomly for 100 different combinations of hyperparameters and see which one works best. Funnily enough, random search generally works better than grid search. So what you usually start doing is start with a random search, so trying lots of different random combinations, narrow it down after like 100 different models, pick one of the best ones from the random search, and then create a smaller grid and exhaustively search across that. So that's one way to do it if you wanted to exhaustively find it. Another way is to just take parameters that work. So find similar research to research that you've, or find similar research or models that are working on problems similar to yours, and just try them on your own problem, see if it works. And if it doesn't, well, then you can adjust it from there. But how to find the best hyperparameters is a open area of research. There's lots of tools to do it, lots of tools to track it, random search, grid search. There's another thing called AutoML. But again, these are lots of things that you'll probably want to look into on your own. My best advice is to use transfer learning. So take a model that already works on one problem and use that on your own problem. However, we're going to cover that in module 6, which is not here yet. That'll be in a future stream. So, good question though. How to find the best hyperparameters. NN.sequential. So we're going to create the second block. Now, we don't necessarily need to look at what's going on over here anymore, because the second block is, we've seen conv2, relu2, conv2 to relu2 to maxpool 2. It's going to be just a replica of conv block 1. So let's create that together now. And then conv2d. And if you're thinking, wow, how does Daniel know like what to use for all these different things? It has only come from practice. I started not knowing, and then I practiced and practiced and practiced, got lots of code. I still don't know lots of things, but because I've done so much practice in writing different neural networks and practicing PyTorch and understanding what a convolutional neural network is, I can now interpret different websites, sometimes fast, sometimes slow. This one I've had a fair bit of practice with, so I can do it quite fast. But research papers might take me a week to fully understand and comprehend. But that's like the nature of a research paper, right? It's only 10 pages, say, of half a dozen researchers who are the smartest people in the field, months and months of work. And so a lot of people will ask me, it's like, how do you understand research papers in machine learning? Well, it's like, with a lot of effort, because very smart people have taken months to create their work and published it to places like Archive. So you and I can read it for free, which is, if you've been in any other fields, that doesn't really happen. I once had to pay $35 US for a medical journal. Anyway, that's beside the point. What we're talking about here is, if you want to get better at replicating neural networks, if you want to get better at writing neural networks, well then write more neural networks. We're going to go relu. So see what we're doing here? Conv, relu, max pool. Conv, relu, max pool. NN dot max pool. Beautiful. And go self.classifier. So what's the classifier? Well, what we're going to do is we're going to pass data through the conv block 1, we're going to pass it through the conv block 2, and then we're going to pass it through the classifier. Now, if we come back to our CNN explainer, the classifier is this output layer here. So what all of these layers here are going to do for us, from the input data to conv1 to relu1, etc., are going to compress a learned representation. Hopefully, it's going to be a good one. From the input data to the output here. Now, this output doesn't really suit us for what we're after. In our case, we want an output of 10 different classes. So we need an output shape of 10. This is where the output shape parameter comes in. If we had 20 different types of images, we might have an output shape of 20. If we had 100, we might have 100 output classes. So I'm working on an app called Nutrify, and in this case, it's going to classify different images of food. But right now, it works on 100 foods. So ideally, by the end of this year, I want it to be working on 1,000 foods. So the output layer of Nutrify works on 100 different foods instead of 10, like we're going to build in the CNN explainer. So let's go back to where we were. We're going to create a classifier layer. It's going to be nn.sequential as well. Now, we might need to flatten the output of our second conv block here. Now, what that means is, let's go back to our CNN explainer. We're going to get an output here that's 13 by 13 by 10. What flatten is going to do is flatten this 13 by 13 into, what's 13 by 13? 169. a vector of size 169. Why do we do that? Well, because the final layer here that we want to do, which is nn.linear, likes data to be in a particular shape. So the in features here is going to be what? Well, I'm going to give you a little trick to figure this out, because in essence, before you actually pass data through a network, sometimes you don't know what shapes you need. So how do we figure that out? Well, we build the network up until the point that we don't know what shape we need as an input shape, and then we put some data through it, and we test through trial and error what shape we need. Well, at least that's how I do it. If you have a better way of doing that, please let me know. So the out features here is going to be output shape. Do you notice there's a trend here? All we've been doing is manipulating data in some way, shape, or form. All these layers do is manipulate data into the size and shape that we want. So now what we need, because we've subclassed torch nn.module, we need to write, we've initialized our neural network. We've got all the components here. But now we need a method to pull them all together to do our forward computation. Let's look up an image of a neural network. When I say forward computation, I mean forward through the network. So we have an input and it goes through this way to the right to an output. So we have an input layer, which is our images go in, our image tensors. We have hidden layers such as convolution, such as ReLU, such as max pool. They do some form of numerical calculation to hopefully learn a learned representation of our input data. And then we have an output data. The forward propagation is when we have data that goes in through all of these layers and then out the other side. So we need to create, every time you subclass torch nn.module, you need to create a forward method, which defines the forward computation. And we're going to put self here. Our forward method is going to take an x. X represents our input data. You could use almost anything here. You could go input data. But it is generally best practice, and you'll see this quite often, is to use x as a representation of the input data. So then we're going to go x is equal to conv block 1. We're going to pass x to that. And then we're going to go x is equal to conv block 2, pass x into that. And then x again is equal to classifier with x. Do you see what we've done here? Self, and we need to do self here, otherwise it'll error. Self and self. Do you see what we've done? So we've defined a sequential computation through different NN layers, neural network layers, in conv block 1. We've done the same similar setup in conv block 2. Then we've done again the same similar setup in self.classifier. This kind of pattern, this design pattern, will follow you throughout many different neural networks unless the fundamental way that neural networks are built changes. Is that you define some sort of existing layers, and then within the forward method, you define how those layers interact with each other. In our case, we're just passing an input x through the convolutional block 1. It's going to perform computations, same as the computations that we've seen on the CNN Explainer website. PyTorch has implemented these behind the scenes for us, so thank you, PyTorch. Then we're going to take the output of conv block 1 and pass it into conv block 2, again, manipulating the data over and over, trying to create a learned weight and bias, weights matrix and bias vector within all of our layers, and then finally passing it through our classifier. And then hopefully we can use the output of our classifier as some form of intelligence. So, with that being said, let's see where some errors are. And I mentioned a trick to figure out the shape that you need to put in between every layer. Well, we can go here. Let's figure out the output shape of the first conv block, print x.shape. And we're going to figure out the shape of the second conv block. And we'll figure out the shape of the final classifier here. Wonderful. And then do we need to return x? I think we need to return x. Wonderful. So we've got our MNIST model. A lot of code there, but with a fair bit of practice, you can start to code these models, or you probably are already starting to code these models if you're watching this video. So let's go create our model. Model equals MNIST model, and we're going to send it to the device. So our device is equal to what? CUDA. So we're going to put our model on the GPU. And then we go model. Oh, what happened here? Oh, excuse me. I need to create there. And we have some values that we need to pass to our model. Input shape. Input shape equals, what's our input shape going to be? It's going to be 1 because we're dealing with grayscale images. What are the hidden units going to be? If we were dealing with color images, this would be 3. Hidden units is equal to 10. And the output shape is also going to be equal to 10. Why are we using 10 and 10? Well, because we're replicating this neural network here. And they used a shape of 10 here for the hidden units. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And they have an output of 10 because they're dealing with 10 different classes. And in our case, we are dealing with 10 different classes as well, except ours aren't images like this. Ours are handwritten digits from 0 to 9. So let's come back here and let's see if this works. Oh, what did we get? List is not a module subclass. I'm going to come back and fix this error in a minute. I'm going to go to the bathroom. Be back. Okay, you know what I think we got wrong? I don't think our sequential layers need a list as input. So sequential, nn.sequential, because that's what our error is. List is not a module subclass. So that's telling me, type error. Where are my lists in here? Let's give it a shot. I don't know if this will work, but I'm going to try it anyway. Remove list. That's the beauty of live coding, is all the errors are included. So I think sequential might just take things how they are, not as the form of a list. Is it working? It looks like it might be working because it's sending it to the device. Yes! Woohoo! Look at that, everyone. We now have our first model. Well, the first model of this stream. And so let's get model.parameters. Wonderful. So here is our... let's get model.stateDict, actually. StateDict is going to have all of the parameters our model is going to try and learn. Okay, so this is, look at all this. This is our model has been initialized with random weights. So conv_block1.0.weight, it has this big tensor. And if we go scroll down, it has a bias vector. And then conv12 has another weight matrix or a weight tensor. I use the term matrix and tensors synonymously, like quite interchangeably. Really, these are all tensors because they're multidimensional. We have another bias, they're all tensors because they're in PyTorch, and PyTorch's main data type is torch.tensor. And then we have another weight. So these are all the random patterns that our model has been initialized with. And so the whole goal of neural networks is to adjust these random patterns, start with random numbers, and adjust them to be representative of some data. How do we do that? Well, we're going to pass them through these layers. We're going to perform mathematical operations on our data, and we're going to see how those mathematical operations interact with these random parameters. And then we're going to see what our loss value is, how wrong our model is. Then we're going to use our optimizer to slightly adjust each one of these values to hopefully better represent our data and lower the loss function. Look at all that. So that's too much for us to go through. Like already, we've built a relatively small neural network, and already there are so many numbers here going on, I can't wrap my head around all of them. So if you can understand all of the numbers here, well, credit to you. But personally, I can't, so I'm just going to leave that there. But that is what you just have to remember is happening when we train our neural network. These random numbers are going to try and be adjusted to better represent our data. And look at that. We've built a small network. Our network's only about 8 layers. Modern neural networks are like 100. Same principle applies though. Start with random numbers, adjust them to better suit your data. Let me comment this. To find out what patterns our model wants to learn. Okay, there's our model. Now, how do we work out, I'm going to tell you straight up that this is probably wrong. How do we work out the shape that we need to go through? Well, let's do a dummy forward pass. So what data is our model expecting? So right now, our data is of shape 1, 28, 28. This might be an actual problem later on because we've built a model that is fitted for 64, 64. But let's see how we can fix this. So let's create a dummy piece of data. Try a dummy forward pass to see what shapes our data is. So when we do a dummy forward pass, we're going to do model X, but we don't have an X, right? So our model is going to take X and it's going to perform the forward method here because we have X here. And it's going to go through all of our layers that we defined. So first, we need to create a dummy X. So dummy X equals, we can go torch.rand, and we're going to create a tensor in the shape of the same as our image. So let's see what happens here. And we're going to pass it in here. You see what happened? Let me just show you dummy X before we do that. We just created a random variable in the same size of our images, 1, 28, 28. So this is one way to troubleshoot your models. Just pass random data through and see what happens. Oh no, what's happened here? Expected 4-dimensional input. Excuse me, my throat is quite scratchy at the moment. It's not COVID, don't worry. Should I have said that on stream and I'll repost this on YouTube? It's going to get flagged for saying the C word now. Runtime error. So this is another big error in deep learning and machine learning in general is, as I said, shape mismatches. So what shape is your data versus what shape your layer is expecting versus what shape you'd ideally want. So let's add an extra dimension here to convert our 3-dimensional input to 4-dimensional. So I'm going to go unsqueeze dim equals 0. And then if we go there, comment out that, comment that, what do we get? A typo. Classic. Beautiful. And then if we go dummy x dot shape, wonderful. 1, 1, 28. So now we've got a 4-dimensional tensor. This is just the equivalent of making one random image. But it's an important concept to understand is when you're troubleshooting a model, you're going to get many errors if you have the wrong shape. Let's see what happens here. Oh no, what's happened here? Oh, another error. This is another common error that we get in deep learning, or PyTorch especially. What is it saying here? Expected all tensors to be on the same device, but found at least 2 devices. So we have, oh my goodness, we have our model is on GPU and our data is on CPU. Oh, forgive me. So let's put our data to the GPU as well, or to the target device. That's a better way of putting it, because that is device agnostic code. Now let's see what happens now. Do we get an error? Oh no, here we go. Okay, So mat1 and mat2 shapes cannot be multiplied. So, oh, okay, so we've got some output sizes. Let me just write this. F equals output of conv block 1 x.shape, and go here, output of conv block 2 x.shape, and then output shape of classifier x.shape. Is that what we want? Yes, it is. Well done. All about the input and output shapes, ladies and gentlemen. This is what we're troubleshooting. Boom, boom, boom. What do we got? So we have output shape of conv block 1 is this. So we've manipulated our data in some way, shape, or form to end up like that. Output shape of conv block 2. We have torch.size 1077. But we don't get an output shape of the classifier layer. So that is a way of troubleshooting where in our model that we're getting errors. So see how I put these print statements after each layer? So that's what we're tracing where our data is going through the forward layer. Now this is a big problem that you're going to come across in many of your neural networks is tensor shape mismatches. I come across this error every single day. So being able to troubleshoot such a thing is an important skill to have. And how do you troubleshoot? Well, one good way is to use print statements. What we're having an error here is matrix 1 and matrix 2 shapes cannot be multiplied. 1 times 490 and 10 by 10. What's going on here? Well, I think where does this number relate to? If we go 10 times 7 times 7, what do we get? Is that going to line up with what we need? Maybe it does, maybe it doesn't. And what if I remove this flatten layer? Let's just explore with some things. Because truly, okay, 70 times 7 and 10 times 10. Or what if we keep the flatten there and go back? Where are we getting this idea? So 490, how do we get these things to line up? What are the rules of matrix multiplication? We need the inner dimensions to match. So where is this 10 coming from? Let's have a look, eh? Let's change this to in features. Oh, could that be where our error lies? Let's change this to 758,594. Where does this number line up? Oh my goodness, look at this. 490 and 758,594. So if we change this to be what? How could we get this matrix multiplication to line up? Well, we want... Maybe we change this to 77. Well, what do we get? Oh, no, we don't get it. Okay. So, where does this 490 come from? Well, let's have a look at the output shape of conv block 2, because why would we look at that? Because the output shape of conv block 2 is going to be the input for the next layer, which in our case is the classifier. And so we might want 10 times 7 times 7, which equals 10 times 7 times 7, which equals 490. Beautiful. So how would we test this? Let's go here and maybe we go torch.rand size equals, we'll pass that in. And what do we get? Dummy x2. Now dummy x2.shape. Now what happens if we pass dummy x2 through a flatten layer? Flatten layer equals nn.flatten, and then flatten layer dummy x2. What do we get? What's the shape here? There we go. That's what's up, baby. Okay, so that is where this number is coming from. We have a conv block 2 passing data into our classifier layer, and our classifier layer is trying to flatten the data from a matrix of 1 times 10 times 7 times 7, that's a tensor really, into 1 times 490. So that means our last linear layer needs to have an input shape of 490, because if 490 was here, does our matrix multiply work? Remember, matrix multiply, for it to work, which is what's happening on the inside of nn.linear, the input or the inner dimensions need to line up. So let's put that in there. Let's put hidden units times 7 times 7. Now, why are we doing that? Well, because hidden units is 10, and the output here is 10, 7, 7. Now, you might be saying, Daniel, how did you know where to get that number? Well, again, that's through a lot of trial and error to figure out what shapes are where. And through my knowledge of matrix multiplication, which we've covered in a previous set of videos, is that the inner dimensions must match. All right, and so I took my inkling from this going, where does this number come from? And then you can troubleshoot by printing different shapes. Now, of course, these values here, they might change if we were using a different size image. So let's change this. 64, 64. What do you think is going to change? If we have 64 by 64 image like we have here, how do you think the shapes are going to change? Oh, excuse me. Let's run that. Oh, look at that. 16 and 16. Now, if we increase this again, 224, which is a common image size, 224, what happens? Oh, they change again. So that is just something to be aware of. Remember how we talked about a neural network is compression, but it depends on the level of compression will also depend on what size your inputs are and what size your different values are of your hyperparameters. But the whole overall premise is that a very important thing to be aware of in machine learning and deep learning is what are your input and output shapes between each layer. How do you troubleshoot that? For me, I like to troubleshoot it through printing out the input and output shapes of each layer sometimes. Once I've had a little bit of practice, I can kind of skip a few steps because I know where to look. But just keep that in mind. Input and output shapes between each layer. Let's run this. Look at that. Look at that. We got a full run through of some dummy data through our model. Output shape of conv block 1. Our data gets transformed from 128, 28 to 110, 14, 14. And then it goes through conv block 2. It goes from 110, 7, 7. So it's gone halved. So 28 to 14, halved. 14 to 7, halved. And then the output shape of our classifier is 10. So one value per class that we're working with. So this is a value for 0, a value for 1, 2, 3, 4, 5, 6, 7, 8, 9. And of course, this is all going to be random jumbled up numbers because we just passed a dummy tensor through our model, and our model is not going to have any predictive power because it is using random numbers to generate these outputs. So now, with that being said, it is time to train our model. So train the model you built in exercise 8 on CPU and GPU and see how long each take. Okay. Let's do that, hey? So first we need train on CPU. And then we're going to train on GPU. So I'm going to get my model code here. So model CPU, and I'm going to put this on the CPU. And then I'm going to write a training loop. And I'm going to time this. I might say train the model you built in exercise 8 for 5 epochs. So not too many. Training loop. So 4, we'll go epochs equals 5. So 4 epoch in range epochs. And we might put in here TQDM because this is going to measure the progress here. So from tqdm.auto, if you import tqdm.auto, tqdm is a progress tracker in Python. So tqdm comes installed on Google Colab. There we go, tqdm. If you use, you could just do from tqdm import tqdm, but if you do auto, it recognizes whether you're running tqdm in a script, so a Python script or a notebook, and it just has a little bit of different formatting if you're using it in a notebook. I prefer to do it in a notebook or use the auto version for my code. So we're going to put the model in train mode, or the CPU model. Now we're not going to cover too much on the training loop because we would have covered that in a previous 0.1 and 0.2. So if you'd like to be refreshed on that, we've got Learn PyTorch.io. You can see the training steps in here. But now, since we're dealing with batches, we have to go x for xy in train data loader. Let's go. No, that's not what we're going to do. We're going to go that for batch xy in enumerate. That's what we'll do. Train data loader. Let's do the forward pass. Forward pass. So we're going model CPU. We're going to pass it the X data. Now we might just make sure that our data is on the right device. Put data on CPU. xy equals x dot to CPU, y dot to CPU, and then we're going to do the forward pass on x. So y pred equals model x CPU, and then we're going to do loss. Oh, we don't have a loss. Let's create a loss. Create a loss function. So loss fn equals nn dot. Let's do cross entropy. Cross entropy loss. Is it cross entropy loss? I'm having a mind blank here. Yep, cross entropy loss. I thought so. And then what's our optimizer? What optimizer do we want to use? What did we use in the notebook? Optimizer equals wow. Did we not set up an optimizer? Oh, there we go. We're going to use the same optimizer here. So SGD, and we're going to go model CPU dot parameters, and the LR was 0.1. Create a loss function and optimizer. I'm just going to bring this down into the next cell. So writing a training loop, and we'll go loss calculation. Because what's the steps in a training loop? We do the forward pass, calculate the loss, optimize a zero grad, loss backwards, optimize a step, step, step. That is the PyTorch optimization loop theme song. So loss equals loss function on y pred versus y. And then we're going to go optimizer 0 grad to 0 the gradients, optimizer 0 grad, and then we're going to go loss backwards, loss backward, and then we can step the optimizer. Optimizer.step. Beautiful. And now we can do the testing loop. So we'll go maybe we'll put the model CPU.train inside that. The testing loop, we can go for batch x, y, test data loader, and put model in eval mode and turn on inference mode. Because we switch the model CPU to eval, and we go with torch.inference mode. Whenever we're making predictions, we turn on inference mode. We're going to go test pred equals model CPU on X. Oh, we should make sure that the data, make sure test data on CPU. And is this going to mess up if we go, I might put this as X test just to differentiate what we're doing. Yeah, I think that's a good idea. X test, Y test equals X test dot two. We're going to make sure it's on the CPU. Y test. And we're going to compute on X test. And then we'll calculate the loss. Loss function equals test pred versus Y test. And then I think we can print out what's happening. Yeah. Print out what's happening. So we can go we can go epoch equals epoch, and then loss equals loss, and we might just get this to 2 or 3 decimal places, and then we'll go the test loss here, which is test loss, and we'll get that to 3 decimal places as well. Beautiful. Is this going to work? I have no idea. We put the model on the CPU, created a training loop, train, put it to CPU, do the forward pass, calculate the loss backwards, step the optimizer. Now we go through the testing data. Let's just see what happens. Oh my goodness, we're working. But we've got so many printouts here because we left the printouts in our model. I'm going to just comment these out. Wait for that to finish training. Oh my goodness. In the meantime, while we're waiting for that to finish outputting, I'm going to convert this to GPU code. Train on GPU. Oh, and we also want the print function to be outside. We only want the printout to come for each epoch. Training loop. So we're going to put this to the target device. Device equals CUDA. If torch.CUDA is available, else CPU. And we need to change this to GPU. GPU. We need to change this to device. device, and we'll put this on device as well. Device. And I believe that should be good enough. Oh, model GPU. Might see if I can stop this. These print statements and training is really slowing us down. Have we got that correct? Oh, we could cumulatively. Let's do that. Plus equals loss divided by batch number. Because that's going to accumulate. So every batch, we're adding the loss, but we want to divide it by train loss equals train loss plus loss divided by batch. It's going to give us the average loss per batch. Test loss equals 0. And then test loss equals test loss plus test loss. Test loss total. Equals test loss plus test loss total plus test loss divided by batch. Now this is taking quite a while to calculate on the CPU, so just keep that in mind. Oh, there we go. We've stopped. We'll run this again. See what happens. Oh, I didn't update these. Train loss, and then test lost total. Oh yes, you're right. Thank you. Unstable juice says plus batch plus 1. Otherwise, we're going to have a divide by 0 error. We should find out that in a second. Thank you very much. Okay, so we're taking about 35 seconds per epoch here. And then test loss equals 0. So this is, we're just calculating the loss per batch. That's what we're doing here with this code here. Train loss, and we're just dividing it So at the end of each epoch, we want it to print out the average loss per batch over that epoch. So ideally, we'll see these loss values going down. Beautiful. Good morning, Akash. How are you? Happy Good Friday, my friend. So this model's training on the CPU. It's going to take about, what's 5 times 30 seconds? About 3 minutes or 36 seconds. So this is exercise number 9. Oh, we haven't got too many left. Oh no, why has it started again? Where's this second? This should only be running 5 epochs. Oh, is it because I've got time it there? Let's figure it out. How to time how long a Jupyter cell runs for. Time. Okay. We'll just run that again. And I think time it was going to run multiple loops of the same thing. Okay. Don't worry about that. We'll just run it with TQDM. Cell magic starts with double percentage. Oh, why are we getting a loss value of 0? That shouldn't be the case. We've got something wrong with our loss calculations here, everyone. Let's jump back into the notebook and use our reference code. Ah, there we go. Okay, I'm going to readjust this. Let's get this out here. See, this is why you write code and reference it. This is what I would do if I ran into a trouble step. I would reference my own code that I wrote previously. So train loss, we're just going to go plus equals loss. Make sense? And then adjust train loss for number of batches. So train loss length of the train data loader. Testing loop. So with torch inference mode, let's tap this across. Turn on inference mode. Test loss total, we're going to add this up. Plus equals the test loss. And then we're going to test loss equals length test data loader divided by length of the data loader. Test loss total. And then we can print out what's happening. Beautiful. All right, let's see how this goes, hey? We're going to move on to the GPU now too. So the train loss, we're going to leave that train above. Train loss is going to go plus equals loss. Then we're going to adjust it. Adjust train loss to number of batches. So train loss equals, or divide equals, length of the train data loader. And then the same down here, test loss total plus equals test loss. And we're going to slightly rearrange this. Put the model in Google Colab has a good error statement now. Model GPU, and now we can adjust test loss total for divide equal length test data loader. We got lost going down. Yes, we do. Look at that, team. Okay, beautiful. So, took us a few goes, but we got there in the end. That's the beauty of live coding. And that's what, if you're watching this video in the future, seeing how to go through these exercises, this is the kind of stuff that you're going to face. Writing some code, it not working, and then trying to fix it. So let's just let this finish out. And then we'll train it on the GPU, see what happens. And then we'll see, make predictions using a trained model and visualize at least 5 of them, comparing the prediction to the target label. Okay. And then plot a confusion matrix, comparing your model's predictions to the truth labels. Create a random tensor of shape 1, 3, 64, 64. And then use a model similar to the trained model from Notebook 3 to make predictions on the test data set. You know what? I think we don't need this last exercise because we're going to do so much. I think that I'll leave that as an extension. But we'll get through these. This one, and then this one for this stream. Okay, so wall time was 2 minutes 58. Let's see if this changes when we go to CUDA. So do we have the model and the GPU? Yes, we do. Model GPU. Do we have the data on the GPU? Yes, we do. Do we have the right model here? Yes, we do. I might put this just up here. Put data on target device. Do we think it's going to train much faster on the GPU? Okay, so testing loop, we put the model in eval mode and turn on inference mode. Yes, we do. We loop through the test data. Do we put the test data to the device? Yes, we do. Do we use the model GPU? Yes, we do. Okay, let's see what's going on. Oh no. Type CUDA float tensor and weight type torch float tensor should be the same. Where do we have an issue here? To device. Oh, here we go. We forgot that. Of course we did. Should be the same. Oh, okay. Is it because we've... Oh, this should be GPU. My goodness, did you catch all of these? We should functionize this so it doesn't give us so much grief. Okay, let's see what happens with this. I'm going to go to the bathroom again. I'll be back in a second. Oh, training is much faster on the GPU. We have a wall time of 42 seconds versus 2 minutes 58. So, well done to the GPU. And we end up with a test loss of about the same, 0.37 and 0.36. Okay, beautiful. So let's move on to making some predictions with our trained model and visualize at least 5 of them comparing the prediction to the target label. Okay, how about we do that? So, make predictions with the target model, with the trained model. So, ypreds. Let's just try to make one prediction. We'll get a test data. 0, 0. What happens if we put this just straight through our model? This is a test image. And then if we go im show, test data, is this going to be the wrong size? Yes, we need to squeeze this. Okay, what if we put that straight through our model? So model, we'll go the GPU model on test data 0, 0. So we're hoping for a 7 here. Oh no, we need to expand the dimensions on our input data as well. So we need to go unsqueeze dim equals 0. We need to add an extra batch size dimension onto this. Expected all, oh, we need to put it on the, oh, of course we need to put it on the GPU. Come on, Daniel. Okay, there we go. Okay, we get some logits, because the logits are the raw outputs of our model. So how do we convert these into, so model pred logits equals that. And then we're going to go model pred probs equals torch.softmax on model pred logits, because we want to go from logits to prediction probabilities to prediction labels. So let's do that. Model pred logits, and we're going to pass dim equals 1, and then we're going to go model pred label equals torch.argmax on the model pred probs dim equals 1, and then model pred label, which is 7. Yes, look at that. We trained a model and we got to predict it on a 7. Friends, look how far we've come. From loading a data to coding a PyTorch model, loading a dataset, sorry, to now we've trained a neural network to predict on handwritten digits. How cool is that? So let's make a plot version of this. So num to plot equals 5. So we want for I in range num to plot. Let's go image equals test data 0 or I 0, and then label equals test data I 1, and then we go make prediction on image. So model pred logits equals model GPU on image dot unsqueeze dim equals 0, and of course we have to send it to the right device, and then model, and I'm going to write here, make sure image is right shape plus on right device, and then we're going to go model pred probs equals torch dot softmax model pred logits, the first dimension, and then we're going to go model pred label equals torch.argmax model pred probs dim equals 1, and then plot the image and prediction. So we can go plt.imshow image.squeeze, and we want to actually plot.figure, create a new figure each time, and then we're going to go plot.title. Let's do a nice title here. We'll format that, and we're going to go truth will be label, and then we're going to go pred will be model pred label. We'll have to be sure to pass this to the CPU because matplotlib doesn't deal with things on the GPU, and plt.access is off, and we want to make sure the CMap here is gray, and I'm going to do the same for this one up here. CMap equals gray, black and white images. We predicted a 7, and now let's try it here. Oh, look at that. Oh, and we're going to get just the item here. plot axis equals false. Yes, look at that, everyone. Oh, look at that. Truth. We trained a neural network to predict. We go to 7, we go to 2, we go to 1, we go to 0, and we go to 4. Now, of course, you could scale this up to do 100 different numbers. You could scale it up to do random different numbers. So get image and labels from the test data. Now, this is making predictions on a model, images that our model has never seen. So this is the beauty of machine learning and computer vision, right? The whole premise, what we've just done, is exactly what happens in larger scale computer vision problems. You have some sort of input data set, in our case, handwritten digits in the form of tensors. We convert them into data loaders, which are usable with our model that we've built. Now, we could build this model from scratch, or we could pick a model that we've seen work on other similar problems, right? And then we train the model by going over the training data set. We try to minimize a loss function with the help of an optimizer. We do the forward pass, we calculate the loss, we zero the optimizer gradients because the gradients are going to help us reduce the loss if they're moved in the right direction. And that's what backpropagation does, calculates the gradients of all of the parameters in our model. The optimizer updates the parameters in our model to hopefully lower the gradients or lower the direction of where the gradient is heading. And then we do prediction, and we can test how fast our model trains on the CPU using time. We could also use TQDM to do our progress bar. We do the same thing on the GPU. We find that it trains faster on the GPU. Won't necessarily always be the case, but because our data set is quite large, 60,000 training images, we get quite a significant speed up when we use a GPU. Then we make predictions on it, and they work. So what's the final one here? Let's make a confusion matrix, hey? Plot a confusion matrix comparing your model's predictions to the ground truth labels. Okay, how might we do this? So make predictions across all test data. So, so we need to get ypreds. So let's use model GPU .eval with torch.inference mode and go ypreds equals. How did we make a confusion matrix in here? Oh, we need to import ML extend. I'm going to get that in here. And I'm also going to import this in here. And then we can make predictions. Yeah, okay, so we need to loop through the test data set. Okay. So let's go. We can do this. So ypreds equals an empty list. Turn on inference mode. So we want to go for enumerate test data loader. We want to make a prediction on every single test sample. So forward pass, ypred, logit. So that raw outputs of our model are logits. So model GPU, we're going to predict on X. I'll make sure data on right device. So X, Y equals X.2 device, Y.2 device. and then we want to logits to pred probs to pred label, y pred label equals model pred logits, because these are going to be in batches, equals torch dot argmax of torch dot softmax of y pred logits on the first dimension of this is also on the first dimension, and then append the labels to the preds list. Then we go y preds dot append y pred labels, and then we're going to go y preds equals torch cat y preds, and then we're going to go print out the length of y preds. So we want to go tqdm here, import tqdm.auto as tqdm. This is going to make some predictions. Module is not callable. What do we got wrong here? Oh, from tqdm. Import tqdm. Beautiful. That worked very quickly. 10,000 predictions, and we have 10,000 predictions. So let's have a look at y preds. Beautiful. And so now we need to compare these to our test data loader. We might just do the predictions again to get the y true. So test data dot targets. Okay, beautiful. And y preds 10. We'll get this onto the CPU. Beautiful. Okay. Now let's just see if we got the right stuff. Let's create a confusion matrix. So we can use ML extend to create a confusion matrix here. So let's have a look at ML extend plotting confusion matrix. So this is ML extend, a great library for doing some extra things in machine learning that you might not always do. Plot confusion matrix. What have we got an example of? So I need to make a confusion matrix in some way, shape, or form. Let's go back. How did I make one here? Plot confusion matrix. Oh, torch metrics, we use the confusion matrix. Okay. Import confusion matrix. So I'm still getting around using torch metrics. So set up confusion matrix. So we need to confmat equals confusion matrix, and we pass it in num classes equals length class names. And then we can create the confmat tensor by going confmat y, or the preds equals, we have y preds, and then the target equals test data dot targets. And then we can plot the confusion matrix. I'm going to go fig ax equals plot confusion matrix Conf_mat is going to be our conf_mat that we just created above. This up here. Is my head in the way? No, this should be all right. And then class names is going to be class names because we've set that up before. Equals class names. And then fig size equals 10.7. What do we get? Oh no. Num classes. Oh, what did we get? Confusion matrix has no type length. What did we get wrong here? Oh, conf_mat tensor.numpy. There we go. Beautiful. Look at that confusion matrix. So confusion matrix is telling us where our model predicted the wrong numbers. So it looks like we did pretty darn well across the entire data set. So we've had a few instances here where it mixed up a 3 as a 7, so 6 times. We've also had a few instances where it's mixed up a 9 as a 4. Okay, but for the vast majority of classes, it gets the right thing. It's got a few examples where it predicted a 7, but it was actually a 9. And what are these 5s up here? It predicted a 7, but it was actually a 2. And it predicted an 8 when it was actually a 2 as well. Okay. So a few things, we're just getting confused, but that's pretty darn good across the entire 10,000 examples. And so finally, we have create a random tensor of shape 1, 3, 64 and pass it through a conv NN conv2D layer with various hyperparameter settings. These can be any settings you choose. What do you notice if the kernel size parameter goes up and down? And then finally, number 13, use a similar model to the model trained from Notebook 03 to make predictions on the test Torch Vision datasets fashion MNIST dataset. I'm going to leave this one as an extension for this video, but I'll put some code in here before I post the solution. How about we finish on this? Random tensor equals torch.rand. I think that'll be good enough for a stream for this video walkthrough, don't you? We've covered a fair bit. You could do this one by looking at this notebook here. So let's just finish on this. And then random tensor dot shape. Wonderful. And let's make a conv layer equals nn conv d 2d. In channels is going to be what? Needs to be 3. Out channels can be whatever we want. Let's just try 10. And then we can go kernel size equals 3. Let's make it stride equals 1. And then padding equals 1 as well. And what happens to the random tensor as we pass it through our conv layer? So let's go print random tensor original shape equals random tensor dot shape, and then go random tensor through conv layer. This is to illustrate what's happening as our tensor goes through a conv layer. And then print random tensor through conv layer shape. Random tensor through conv layer dot shape. Beautiful. What happens here? Has no... Oh, typo. Did you catch that? So if we pass it through... Oh, we get nothing changed. Oh, except for this part here. The 10. It's gone from 3 to 10. Why is that? Because we've got 3 to 10. Now, what if we change this to 100? What happens? Oh, we get 100 there. And what if we change the padding to 0? Oh, we get 62 there. What if we change the kernel to 5? We get 60. Okay, and what if we change the stride to 2? Oops, excuse me. Oh. 2. Well, we get 30. Wow. Oh, 31. And what if we put the padding back up to there? We've halved our image shape. Wonderful. Now we put this to 64, 164. Now you see what happens when we just put a tensor through our conv layer? This is just a way of illustrating what's going on in the CNN Explainer website. Remember how I said neural networks are compression? So what we're trying to do is adjust the hyperparameters of the conv layer to somehow compress the original features of an image into a lower dimensional space. So by the time it gets to this output layer, we've gone from 64, 64.3 to some lower level feature vector that we can use to make predictions on. So have a play around with that and give number 13 a go on your own. Again, you can see the code for all of this in learnpytorch.io at number 3 for computer vision. There's a lot more stuff in this notebook here than what we've gone through. All we've done in this one, in this stream, in this video, is go through all of the exercises here, of course, except for number 13, but I'm going to leave that as an extension for yourself if you're watching it at home. And yeah, with all the things that we've covered up in this video so far, and of course within the notebook here, you should definitely be able to do number 13. You may take a few goes to give it a shot, but hey, that's what it's all about. Keep practicing, keep learning, keep creating, and I'll see you guys in the next video. I think the next one, if you're following along with the course series, will be PyTorch custom data sets. But thanks for tuning in, and I'll see you next time. Happy Good Friday.